everyone. I'm Shravana Krishnamurthy, Director of Engineering for the Core Data Platform team at Cardlytics. I'm excited to share with you today the insights and lessons we've learned as we've modernized our data platform. We'll dive into how we've leveraged some of the open source technology, such as Hoodie, along with the AWS tech stack to transform our data platform. I'll start by giving you a brief introduction to Cardlytics and what we do. Next, we'll dive into the purpose behind building our data lake. Then I'll talk about our journey in moving towards a data mesh framework. Finally, I'll share some key learnings from operationalizing our data lake itself. We are an advertising platform integrated into the digital channels of major banks. In short, we deliver cashback and reward offers through ads on the apps and websites of the leading banks in both United States as well as UK. Uh, we basically leverage purchase data from these banks. We gain insights into where and when customers shop both online and in store. And these insights allow us to identify opportunities, target bank customers effectively, and measure the impact of our ads on sales itself. Uh, Currently, we operate in US and UK with about 165 million monthly active users in the US and visibility into one in every two transactions that take place across the country. Business works with data from three key personas, if you think about it: advertisers, banking partners, and bank customers. So, advertisers use our Ads Manager platform to set up their campaigns and set some targeting criteria. Meanwhile, our banking partners integrate with our APIs to deliver personalized offers to their customers in real time. And as the data platform team, we handle and own ingestion of engagement level and transaction level data from these banks, as well as the campaign data from advertisers. We make this, data accessible to various internal product teams, such as those working on targeting, marketplace optimization, reward processing, commerce graph analysis, as well as some of the analysts itself. Next, I want to talk a little bit about the purpose for building out a data lake architecture. A little bit of the history here, right? Initially, we used to have Vertica to solve and build like large range of problems. Uh, and we had a lot of internal products using it for business critical workflows and analytics use cases. However, this introduced scaling challenges where, compute resources used for all the different use cases started contending and causing production service degradations and delays. And very soon, Vertica became a scaling bottleneck and just was not the right store for things like, raw events data and long historical data views. So this is why we needed to rethink our architecture. An outage or performance degradation in one area, shouldn't really disrupt everything else in the business. So one of the key goals for moving to a modern data lake architecture was separating compute from storage. And this separation basically allowed us to scale resources independently, ensuring better resource isolation and also availability of the data itself. We wanted to basically create a centralized, consistent source of truth for all of the business critical systems and analytics needs. This basically meant unifying the data storage and ensuring, it could be accessed reliably by all the end users. Uh, we had a few use cases where, we would use significant compute resources in order to regenerate a data set every time because there wasn't an easy way to find only incremental changes. So this was another key reason for us, to think about a data lake architecture that supports incremental processing itself. So a significant advantage of this new setup is that we've uh, unlocked that incremental processing capabilities. Uh, by landing both streaming and batch process data into a single storage layer, we've also simplified data management in a way. We can now manage both types of data without requiring separate systems. Okay. Our current tech stack, as you can see, is built on several powerful open source technologies, right? Including Kafka for streaming, Parquet for efficient file storage, Spark for distributed processing, and Hoodie for managing large data sets with incremental processing capabilities. We also use Superset for visualization, which I'll dive into further details in the next section. We've organized our data using the Mendelian architecture, like you can see here, uh, which basically allows us to do progressively processing data through these layers. So we can see the first layer is the bronze layer. So this layer basically holds raw data and events capturing everything in its original form. The next layer is the silver layer. Here we clean and transform the data and use it as a staging data set which has some of the enriched data by joining with the metadata tables and things like that. And finally, it's the gold layer. This is where we store most of our business critical data sets, like current snapshots, aggregated views, data sets that are directly used for like different decision making use cases itself. In addition to this, we also leverage AWS Lake Formation as an out-of-the-box solution to easily load data from both relational and NoSQL databases. It's a simple way to get database snapshots from external systems. Uh, and in terms of query engines, we use Athena as our primary query engine for accessing the data in the data lake, while analysts use Vertica as our dedicated data warehouse. Next, we'll talk about writing to data lake and why Hoodie suited our use cases. Uh, Hoodie basically supports two primary table types, right? Copy on write and merge on read. With copy on write updates to like data overwrite entire files. This is more ideal for like read heavy use cases where like query performance is a priority. So for example, in our case, like most of the aggregated data sets used, for reporting or for like downstream pipelines, it made sense to use copy on write. Uh, Whereas merge on read, on the other hand, appends data or updates to the existing data through log files, and it merges them during reads. This type is suited more for like write-heavy workloads where updates happen frequently. So, for example, real-time streaming data sets where data keeps flowing in with new updates to existing data itself. So in that scenario, we went with using merge on read. In terms of Hoodie writers, we basically have for streaming data ingestion, we use Hoodie Delta Streamer. It's designed basically to handle data coming from sources like Kafka and making it just perfect for like our real-time ingestion use case and processing. For batch processing, we use the Spark data source writer. It pulls in data from the Spark data frame and is highly efficient for handling like large batch jobs. A key part of maintaining data integrity in Hoodie is, ensuring record uniqueness. We achieve this by providing partition key, record keys, and precombined keys, which together help identify unique records and handle updates properly. So this particular feature was very important for us. As a data company, we wanted to make sure data integrity is, the top priority for our data lake. Hoodie also supports a range of operations to manage the lifecycle of our data sets itself, right? Things like insert, upsert, bulk insert, deletion. These are all operations that you would want to, do on your data feeds. So this flexibility allows us to handle everything from like adding new records, reprocessing, updating, setting up retention, things like that. Okay. Uh, Next I'm going to talk about the goals for building our data mesh framework. Okay, so the first thing is we wanted to enable teams to own their own data products. So what does that mean, right? Uh, it basically means you want to empower individual teams to take ownership of their own data products. And this basically encourages autonomy and accountability, allowing teams to manage their data in a way that aligns with their specific business objectives and requirements. Now, by centralizing our data pipelines and table definitions, we also create a consistent approach that enhances, interoperability between teams and ensures like a single source of truth for all of our data assets. The other thing is you want to abstract business logic from compute and storage layers, right? What does that mean? Uh, This means separating the format of our tables from the underlying business rules, right? Allowing teams to, focus on data processing without being tied to a specific storage implementation. This again provides flexibility for us to, make changes and adapt over time on different storage implementations itself. The other key goal was to ensure data quality and functionality. So we aim to implement local integration tests for our data products. This allows, our team to validate their data transformation, business logic before deploying it to production. They basically reduce the risk of errors and, improve overall reliability of the data sets itself. The other thing is you want to establish a robust CI/CD pipeline for all your data workflows. So this ensures that code changes are automatically tested, validated, and deployed, basically allowing you for faster iterations and more efficient development cycles itself. Uh, the other goal for the framework was leveraging reusable optimizations, right? So we can enhance the performance of our data pipelines without having to reinvent the wheel for each new data feed that you create. This includes like optimizing, Spark jobs, scaling pipelines, handling, varying workloads, and implementing a more comprehensive monitoring solution to ensure like operational efficiency itself. Uh, Lastly, we also wanted to automate common operations such as, reprocessing data, handling rollbacks, managing data retention, performing deletions. So automation in these areas like reduces the manual overhead on the teams and increases the operational efficiency itself. Okay, next I'll go into how our framework works. So there are different stages to our framework, and I'll start with the first step. The first step is to define the structure of our data lake tables, right? This includes defining the table type, setting up the partition keys, record keys, ensuring we correctly define what's nullable, what's not nullable. We also set the pre-combined key, to ensure the record uniqueness and decide on the table type, right? Whether you want it to be a COW table or a MOR table, depending on our latency requirements and performance requirements. Next is you would want to define the business logic itself to produce this data set or a hoodie table, right? So we define the business logic that will drive our data transformation. We use Spark SQL to specify how data should be processed from the source tables to the final outputs, and basically applying any necessary filtering logic, joins, aggregations, etc. Uh, the next step is provisioning the resources for the pipeline. So the framework helps us provision resources necessary for the job execution itself. It makes it simple for us to just specify the Spark memory or the CPU configurations and any feature flags needed to fine tune the pipeline performance, right? Sometimes you're trying to make these optimizations that are very specific to certain workloads, and it's always better to put them behind a feature flag such that you can enable them only for the workloads that would require it. Next is setting up orchestration. So once you have the business logic defined, you also want to be able to schedule these pipelines or these jobs to run at a certain frequency. They could be hourly, daily, whatever the cadence could be, right? You want to have a way to define these you know tags, as you may say, right? So our framework basically had all of this DAG generation automated. Next, you would want to be able to define, the test data for the source tables, basically create sample data that closely mirrors the real world scenarios, right? So this helps you ensure that your tests, are accurate and represent actual real world use cases. And also, it enables you to ensure that business logic is correctly applied and catch bugs before they impact production. So that's what this whole end-to-end testing workflow would do for us. The next thing would be to set up alerts and monitoring. We define like some of the key alerts for data pipeline health. These include things like lag alerts to monitor pipeline delays, data freshness alerts to track how up to date the data is, business logic specific consistency alerts to ensure data quality, right? This could be something like, you have raw events. Let's say you have like 10 transactions for today, right? You want to make sure that for today you are aggregating it correctly to be 10, right? You want to make sure it's consistent across all of your pipelines and tables so that, if you have to do any troubleshooting, you have a good way of understanding the data lineage itself. The last thing is about making sure you're deploying via CI/CD. So the pipelines or all of the business logic is deployed via CI/CD. Typically, what we do is use GitHub Actions to automate the deployment process. We also use GitHub Actions to run some of our data lake operations, which I mentioned before. Things like, reprocessing, deletion, retention settings, all of these things are basically defined via our framework. Okay, next I want to cover a little bit about, data quality and monitoring. Um, we basically leverage a superset, like I said, for some of our alerting. Uh, and we use One House Lakeview for us to gain some hoodie table level observability. So things like, partition level statistics on number of inserts, number of upserts, etc. Right? Like you want to know at a partition level what's going on. So this helps you debug and identify any anomalies that you might see. We also use Datadog for some of the other monitoring things like, Spark job monitoring, which helps us quickly triage into why we have some failures. This avoids us from having to load up like Spark history server and, look into like the logs of the executors, right? Sometimes the summary of what you see within the Datadog monitoring dashboard is sufficient for you to further make performance tuning changes on the pipelines. Okay. Next, I want to talk a little bit about, some of the key learnings from operationalizing our data lake. Uh, so the first step in building our data lake table always involves migrating data from an existing data source, right? In our case, it was Redshift. So this, creating that snapshot typically requires us to, have a process in place to unload the data. So we unloaded the initial snapshots of the table into Parquet format, and then we leveraged bulk insert to create our initial hoodie table snapshots. However, what we learned from bulk insert is that it does not deduplicate records. This means any duplicate records that were present in our snapshot source dataset would still appear in your hoodie table. Even though you've defined all of the right partition and record keys, you would still see that duplicate data. And this is a learning for us because obviously our older architecture, we had some of these issues where we had duplicate data we were not aware of, and then this continued to go into our data lake. So this is a good learning. So we handled this by making sure we dedupe the data set before taking the snapshot. Uh, and that's how we resolved it. Additionally, we also learned that bulk insert does not support bucket indexing. So one of the key learnings was like if indexing is a requirement, uh, you may need to consider alternative methods to process your initial load. Uh, okay. Next, I want to talk a little bit about uh, the partitioning strategy that we went with. When using multiple partition columns, such as, in our case, we partition by a bank and date, for example, it's always advisable to apply like a global sort when you're doing bulk insert. This approach helps maintain like optimal data distribution and access patterns in the data set itself. Next, one more thing we learned with Bloom indexes is in order to enhance, query performance, it's good to use Bloom indexes, right? When implementing Bloom indexes, it's crucial to specify the number of entries based on the size of the input file and the average record size. This helps like mitigate some of the small file issues that you might see and make sure that you have a well packed, S3 files. So I would say for better performance during the insert process, we had to set, the copy on write insert auto split to false. Basically, what this does is it disables automatic splitting of input files, which can lead to like improved performance in scenarios where, the data set is already well partitioned. Additionally, we tuned the copy on write insert split size. Uh, Again, this allows us to manage the size of the splits more effectively, optimizing for like the resource utilization during bulk insert operation. Okay. Uh, Next, I do want to talk about some of the Spark bugs we encountered. This was one of an interesting, bug we saw, right? At the surface, it was basically an out-of-memory exception on the executor. We looked at the GC logs and, it showed that there was plenty of heap memory, so it did not make sense why it would run out of memory. The next thing we checked was, all the different executor logs. And what we noticed was that this out of memory exception would happen consistently after opening a new part file that needed to be decompressed with Z standard. So, we basically did some more investigation and we discovered that the issue was caused by a memory leak in the Z standard decompressor. So I have linked both the bug and the Spark issue here if somebody wants to learn more. Uh, while the bug itself had been fixed in the Parquet library, it hadn't yet been integrated into the Spark version that was supported natively on the AMR clusters. So as a workaround, what we did is we switched from Z standard compression to LC4. Fortunately for us, Hoodie offers flexibility in such changes, right? Uh, it would support like mixed compression formats within the Parquet files. So it was a seamless switch for us and it helped resolve the issue. Okay, next I want to talk about Hoodie payload extension. One of Hoodie's core feature is incremental updates, which we leverage heavily for some of our datasets. For example, we receive full snapshot data from some of our banking partners, and we want to only truly, update any records that have changed so that downstream systems that read data incrementally don't, have to deal only with changes and not large amount of data every run. Right. In order to do that, we extended and created our payload class that takes a set of columns and hashes using SHA-256 uh, function, and only if the hash changes will it update the record on the Hoodie table. So if you can see this example here, uh, on day, 1, this transaction 2 came in with a status of pending, but on day 7, it changes to success, right? Assume that you're getting both these transactions every day as a snapshot. Uh, and if you have a lot of downstream systems that are doing incremental reads on your data sets, you don't want to send them a record that did not have any change, right? Incremental processing is that you want to only process whatever changed. So in this case, we basically set up the SHA based on a set of columns that would identify actual changes on that record that we would like to update it for. And we basically, use the SHA-256, and if the hash changes, only then it would go and update. The fact that Hoodie provides this extension on the payload class helps us define this level of, business logic or, changes that we would want for specific use cases. So another payload class we used is the partial update payload for cases when we had to backfill new fields on entire data sets or reprocess and update certain fields due to bugs and things like that, right? So this was very useful for us as we evolved our schemas. It was very useful to have this functionality available. So just to go through this example here, assume you had a table, where you just had these 4 fields, and later you wanted to enrich it by adding a category field to it. You could easily do that using the partial update payload class. Okay. Okay. I want to talk a little bit about our journey of moving from glue to traditional AMR to AMR on EKS. So we initially used glue, but we found it to be more expensive over time. Glue was also lagging behind in terms of like some of the Spark and Hoodie versions, which was a limitation for us. So another challenge we faced with Glue was, troubleshooting out of memory issues. It was just very hard for us to understand what was happening and felt like we had less control over the infrastructure. Then we moved to the traditional EMR, setup to, you know, sorry. To overcome these issues, right, we moved into using the traditional EMR setup where we had more control on the resource type we could use, and our implementation involved bringing up, EMR clusters on demand to run specific jobs, then shutting them down when the jobs are completed. This was an early cost-saving strategy that we used, uh, since we were not like using clusters that were continuously running. And in order to further reduce the cost, we adopted a mixed fleet of spot instances and on-demand instances with auto-scaling capability enabled. And then I think what we learned is that spot instances provided significant saving, though they added a bit of complexity in managing the instance availability. It still worked out well in the long run. Eventually, I think as we scaled further, we migrated to EMR on EKS, which provided like additional cost savings and flexibility for us. This approach allowed us to better manage like resources, particularly with Carpenter, which optimally picks nodes and automatically provisions spot instances where appropriate. So with EMR on EKS, resource provisioning became more logical, right? Allowing us to focus on the job resource requirements rather than like worrying about what EC2 instance you would want to use. Okay, um, bucket index, right? Bucket index was an interesting indexing strategy where Hoodie creates like fixed file groups for partition based on a specified bucket count. We wanted to leverage this for one of our large data sets that was spending a lot of time on index lookups and thereby consuming a lot of memory and resources. So in order to reduce the write latency, we used bucket index and configured like X file groups for partition. While this sounded robust in practice, we basically had a lot of skew in our data set. And what this caused is like large partitions, having too much data and, small partitions having too little, resulting in like very slowdowns. Uh, so what we learned is it's not ideal for skewed data. And, we went with using simple index instead. Okay. Last, I want to talk quickly about like some of the performance tuning strategies that we've used. Uh, a significant improvement came from tuning the shuffle parallelism during insert and upsert operations. By increasing the number of parallel tasks, we were able to like update multiple file groups simultaneously, right? Speeding up the entire process, so bringing down the write latency. This is especially important when dealing with large data sets or partitions because it reduces the bottlenecks during the write operations by better utilizing the available compute resources. Uh, the other thing we also did was we enabled metadata stats on our tables to address like a common bottleneck, like which was time spent, listing files in S3. Without metadata, each query or write operation needs to scan and list all the files in the partition, which can result in like being throttled by the S3 rate limits. By enabling metadata, we were able to like cache file listings, significantly reduce the time spent on this task, leading to like faster queries and updates. One other interesting performance improvement that we did was because of some of the uh, SQL query planner exceptions that we were seeing in our pipelines. Uh, so these exceptions often occurred when like Spark's query planner became overloaded or like complex transformations on our large data sets. So these whenever these exceptions happen, what Spark would do is like attempt to like replan the entire query, leading to like, a longer job run. And sometimes it would also fail, and it was just causing a lot of, delays on our pipelines. So to mitigate this, we introduced checkpoints between critical Spark stages. So by checkpoint pointing, we persist the intermediate data. So in case of a failure or query planner exception, Spark could like resume from the checkpoint rather than replanning and re-executing the entire DAG. So this reduced the need to, recompute entire data frames after failure, saving like significant compute costs and minimizing some of the job reruns that we were seeing. Cool. Think that's pretty much what I had. Thank you for listening. At the same time, I do want to say we are hiring. So we are hiring like data engineers at senior and principal level. So please reach out on LinkedIn if you are interested. Thank you.